Hello everyone and welcome to this source of remote learning. I'm the tutor and the math helper at the Academy, and I'm going to be bringing you guys some extra practice problems during your time in your online education. I'm still trying to figure out the sounds and lighting, so hopefully that'll get better over time. But for now, let's go ahead and jump into these practice problems that I've provided. So these are going to be practice problems on 10.6 alternating series. So the alternating series test, which you should have covered in your lesson, is a summation that sums negatives, positives, and so on, where those signs alternate. So in order to do the alternating series test, there's two things we need to confirm. One, that the terms are non-increasing in magnitude, meaning that a sub k plus 1 is going to be less than or equal to a sub k. And secondly, we need to show that the limit of a sub k as k approaches infinity equals 0. And that a sub k that I'm talking about is like taking the absolute value of this series, what's still left within. So let's go ahead and go over number 1, example 1, part A. It says to determine whether the following series converge. So what we're going to do here, we're going to apply the alternating series test. So I'll just write AST, alternating series test. And looking at this series, my a sub k is going to be, well, the thing that's dictating whether it's negative or positive is this negative 1 to the k plus 1. So if I took the absolute value of that, we would just have 1 over k. So a sub k is going to be 1 over k. Now, our first step of the alternating series test is to show that our terms are non-increasing. So what that means is that a sub k plus 1 is smaller than a sub k. Now if we think back to Calc 1, we can think about having a negative slope. And a negative slope happens when the derivative is negative. So as long as we can show that the derivative is negative, we can show that these terms are non-increasing. So what I'm going to do is I'm going to say the derivative with respect to k of our a sub k term, which is 1 over k. What's that going to be equal to? Well, if you need to think of a sub k as k to the negative 1 and take the derivative, then we would get negative 1 times k to the negative 2, decreasing that exponent. But as far as writing negative exponents go, we prefer to put those as positive exponents in the denominator. So I'm going to change my negative 1 times k to the negative 2 to negative 1 over k squared. Now, you can see that this is indeed negative. I'll go ahead and circle that negative so we can see. So this term is going to be less than or equal to 0, which is negative, therefore it's non-increasing. The next step we need to show is that the limit of a sub k as k approaches infinity equals 0. Well, a sub k in this case is 1 over k, and the limit of that is 0 because as k approaches infinity, we have a finite constant over something that's blowing up. That's always going to go towards 0. So we have our second condition confirmed. Therefore, that's what these 3 dots mean. Therefore, this alternating series converges. And I'll just write converges. So therefore, this alternating series converges. Now, let's move on to B. And B, again, for these 3 steps, we're going to be performing the alternating series test. I just like to write what test I'm performing when I go to figure out whether a series converges or diverges. Now, in this case, if we took the absolute value of this, you can see that the only thing that makes this negative or positive is this negative 1 to the k plus 1. So what I have left is my a sub k that is 1 over k squared. Now, I need to show that this is non-increasing. And again, we can easily do this by taking the derivative. So as long as that derivative is less than or equal to 0, we know that it's either negative or 0, which means our slope is negative or not changing at all. So that would be non-increasing. So taking the derivative again, I'm going to do dk of 1 over k squared. Now, that is like k to the negative 2. So this will become negative 2 over k cubed. And if you need to rewrite these as negative exponents and then convert it back to a fraction, feel free to do so on the paper. And this is also less than or equal to 0 because, I'll go ahead again and circle it, we have that negative there. So this is indeed non-increasing. Now, another thing we need to check is that the limit equals 0 as k approaches infinity of our a sub k, which in this number is 1 over k squared. Again, I know that my numerator is staying the same at a constant of 1, whereas my denominator continues to blow up as we go towards infinity. So a constant over a really large number is going to be a super small number, so that's going to go to 0. So because we meet both of those conditions, this alternating series, therefore, it converges. Now, our last part in example 1 is part C. Now part C, it says negative 1 to the k over the square root of k. Negative 1 to the k is the thing that's determining whether we're positive or negative, adding positives or negatives, summing those up. So we're going to take the absolute value, and that's going to be our a sub k. So doing the alternating series test, our a sub k is going to just be 1 over the square root of k, which I think is easier to think of as 1 over k to the 1/2. So first, we got to show that it is non-increasing. What's one of the easiest ways to do that? Take the derivative. And it's easy to do this because taking the derivative of a problem like this is simple. If the derivative gets really difficult, try a different way. That's something where you can plug in k plus 1 and have your a sub k and compare a sub k plus 1 with a sub k. As long as you can show that that a sub k plus 1 is less than a sub k, we know that it's non-increasing. So that's just another way to think about those. Another way you could show that terms are non-increasing is setting up a ratio with a sub k and a sub k plus 1. I just think the derivative is a surefire way to get there because all we have to do is show that it's negative. So in this case, I'm going to be taking the derivative of 1 over k to the 1/2. This is equivalent to k to the negative 1/2. So k to the negative 1/2, dropping that negative 1/2 down in front, and then decreasing my exponent by 1, this is going to be negative 1/2 k to the negative 3/2, or negative 1 over 2k to the 3/2, which we can see, again, let's go ahead and circle it, is a negative number. So we know that this is less than or equal to 0 because it's negative. Therefore, since the derivative is negative, we're non-increasing. Now, number 2, we need to show that the limit as k approaches infinity of a sub k, which in this case is 1 over the square root of k, is 0. And it is indeed, because as k goes to infinity, that denominator goes towards infinity, whereas our numerator stays at a constant of 1. Therefore, we're going towards 0. So in A, B, and C, all of my alternating series converge. So let's move on to the next page. So the next page dives a little bit deeper into convergence. For alternating series, they're either going to converge absolutely or they're going to converge conditionally. Now, absolute convergence for an alternating series is when the absolute value of that series converges and when just the alternating series itself converges. So if we scroll back up, in A, B, and C, we just showed whether the alternating series converged by the alternating series test. So to show absolute convergence or conditional convergence, we then need to check, because we know how to check these now, because we did the alternating series test, we need to check the absolute values. So if the absolute values converges, it converges absolutely. And if the absolute value diverges, we know it only converges conditionally, because it only converges in the case of it alternating. And the cool thing about this absolute versus conditional convergence, if we can show that the absolute value of the series converges, we don't even need to bother with the alternating series test, because we know that this is going to converge as long as the absolute value converges, that alternating series converges. But we'll go into that and you'll see some examples in this worksheet. So, before we jump into these examples, let's talk about what can we say about this series, negative 1 to the k plus 1 over k squared, versus this series, negative 1 to the k plus 1 over k. Let's first look at negative 1 to the k plus 1 over k squared. Now, if I was to take the absolute value of this series, I would get the summation of k equals 1 to infinity of 1 over k squared. So what do we have? Does this converge or diverge? Do you know off the top of your head? If not, we should practice this, because what do we have here? We have a p series. 1 over k squared is a p series with a p-value that's equal to 2. So because we have a p-value that's equal to 2 for our p series, we know that that is greater than 1. And because it's greater than 1, we know that this is a p series that converges. So the absolute value of this series converges, and if we scroll back up, in part B, we have the same exact series, and we also showed that that alternating series converges. So because the absolute value and the alternating series converges, we know that, let me write this out real quick. Because our absolute value converges, we have absolute convergence. So this series converges absolutely. And you can see if we scroll back up to our little definition box, the absolute value converges, then our overall series converges. However, now this is a question to lead you into thinking. Look at this next one. Let's go ahead and look at the absolute value of this next series, negative 1 to the k plus 1 over k. Now the absolute value of this is the summation of 1 over k as k goes from 1 to infinity, which this is a harmonic series, or if you didn't know that it was harmonic, we could also see and recognize that it's a p series, and this p series has a p-value that's equal to 1. So because that's less than or equal to 1, according to the definition of p series, we know that the absolute value of this series then diverges. So because the absolute value diverges, but remember, if you scroll back up, we did this example in part A. And in part A, we showed by the alternating series test that the alternating series converged. So because therefore, the series converges conditionally. So looking back up at our example box or our definition box, we have that a sub k, that absolute value of the series diverges, and the alternating series itself converges. Therefore, the overall alternating series converges conditionally. So our first series converged absolutely, or showed absolute convergence, whereas the second series converged conditionally. So let's go into example 2. Example 2 says to determine whether the following series converge absolutely, converge conditionally, or they diverge. So what I like to do to make this a little bit easier on myself, because remember, if the absolute value of the series converges, then it converges absolutely, and we don't even need to do the alternating series test. So let's go ahead and check the absolute value of this series first. Well, if I was to write out the absolute value, we get a series where we have 1 over k to the 2/3. And 1 over k to the 2/3 is what? Well, it's a p series, and it diverges. It's a p series that diverges because our p-value is 2/3, which is less than or equal to 1. So I know that the absolute value of my series diverges. Therefore, I'm one of two things. My whole overall series is just going to diverge, or it's going to converge conditionally. But we've completely eliminated the fact that it's going to converge absolutely. So now we need to go into the alternating series test to determine what this series does. So going into the AST, we know that our a sub k, well, we kind of got our a sub k value right up here for us. When we take the absolute value of the series, that's what a sub k represents. So that's going to be 1 over k to the 2/3. Now, do you guys remember what we're supposed to do in part 1? We're supposed to show that the terms are non-increasing. So, showing that these terms are non-increasing, that's as simple as taking the derivative and showing that the derivative is negative. So this is like k to the negative 2/3. So when I take the derivative of 1 over k to the 2/3, I'm going to get negative 2 over 3 times k to the, what's negative 2/3 minus 1? That's going to be a negative 5/3, which is going to be a positive 5/3 in my denominator, which we know it's negative, therefore we're non-increasing. So I'll go ahead and check that we're non-increasing. And let me go ahead and rewrite this real quick to make it a little bit smaller so that I'm not running into my next page. Okay, so we showed that it's non-increasing. Our next step, part 2, is to show that the limit goes to 0 of a sub k, which is 1 over k to the 2/3, as k goes to infinity, or as k approaches infinity. And this is indeed 0. Therefore, since we showed that both conditions of the alternating series test are met, then the alternating series itself converges. So if the alternating series converges and the absolute value of the alternating series diverges, then overall our series conditionally. So we converge conditionally for part A in example 2. Now let's look at B. If I was to take the absolute value of this series in B, I would get a series where k goes from 1 to infinity of 1/3 to the k. And if you're confused on how I went from here to here, we could essentially rewrite this series because I can pull out a negative 1 from this, so this would be negative 1 to the k times 1/3 to the k. And the absolute value, this negative 1, is the only thing that dictates whether the overall series is negative or positive, so taking the absolute value, that would be like a positive 1. So then all we would have left is this 1/3 to the k. And that's just simple exponent laws there. So now that we have our series, well, you should recognize this form of a series. So let's get good at recognizing this. It's not a p-series, but it is a geometric series. And what's special about geometric series? Well, geometric series, we know whether they converge or diverge based on their r value. The geometric series is in the form of a r to the k, and the r value in this case is 1/3. So because our r value is equal to 1/3, that's between -1 and 1. So the absolute value of our r is less than 1. That's just another way of saying that it falls between -1 and 1. Therefore, we know that the absolute value of this series, because it's geometric, we know that the absolute value of the series converges. So because the absolute value of the series converges, I don't even need to do the alternating series test. There's no need for it, because if the absolute value of the series converges, then it converges absolutely. So I'll just make a little note. There's no need for the alternating series test in this case. Because the absolute value of that series converges, it converges absolutely. So if we were to do the AST, let's do it quickly in our heads. We can show that these terms are non-increasing. We could take the derivative, or if you just think about a sub k versus a sub k plus 1, if this was a k plus 1, then we'd have 1/3 to the k times 1/3. So we're taking that original a sub k and then multiplying it by 1/3, so we're decreasing its value. So we know that it's decreasing, and the limit of this as k goes to infinity would indeed be 0. So let's go ahead and move on to our practice problems. Our first practice problem, and number 1, is -1 to the k times k over k plus 1. So what I like to do first is I like to test the absolute value of the series, because if that converges, then I know that we converge absolutely, no need for the AST. So writing the absolute value of this, the only thing dictating whether these are positive or negative is that -1 to the k. So that would essentially be equal to 1 when I take the absolute value. So I'll get k over k plus 1. Now, does this converge or diverge? Well, we need to pick a test to try it out. Our other ones so far on this worksheet have been simple because they've all come out to be p-series or geometric series. But we need to figure out what happens with this series, and it's not a p-series and it's also not geometric. What I like to start with is the divergence test. So if we do the divergence test, all we're going to do is take the limit of what's inside our series. So the limit of k over k plus 1 as k approaches infinity. That's going to equal, well, highest power rule, k to the first over k to the first plus 1. Those coefficients of our k's are 1, so we get 1 over 1, which equals 1. And by the divergence test, that's not equal to 0, therefore, the absolute value of our series diverges. All right, so we showed that the absolute value of the series diverges, which means now we're either going to diverge overall or we're going to converge conditionally. We've eliminated absolute convergence. So let's go ahead and do the AST now. The AST, our a sub k term for the AST, we already got when we took the absolute value of our series, which was k over k plus 1. So a sub k is going to be k over k plus 1. Now remember, for alternating series, we need to show that it's non-increasing and that the limit equals 0. Just because I number these 1 and 2 doesn't mean we have to do them or perform them in that particular order. It just means that both conditions need to be met. And right away, if you look how we did the divergence test up here, that's kind of like step 2 of our AST, but it's not the divergence test, so don't confuse it with the divergence test. But part 2 is taking the limit of the absolute value, or of our a sub k, which is k over k plus 1 as k goes to infinity. And wait a second, we got that that wasn't equal to 0, it's equal to 1. Therefore, right away, we fail the alternating series because this limit doesn't equal 0. Failing that alternating series means that overall, we're just going to diverge. So the series diverges in number 1. And if you didn't realize you could do condition 2 before condition 1, you probably jumped into trying to show that it was non-increasing. So is it non-increasing? Well, if we take the derivative of k over k plus 1, we can go ahead and do low d high minus high d low all over low squared. Quotient rule, right? So low, k plus 1, times the derivative of the high, 1, minus high, which is k, times the derivative of low, 1, all over low squared, k plus 1 squared. This is going to be equal to k plus 1 minus k, which is 1 in our numerator, all over k plus 1 squared. Right away, this is not less than or equal to 0. Therefore, again, it's not non-increasing. It's actually, the derivative's positive, so it's going to be increasing. So it also fails number 1 in this case. But as long as it fails one of them, we can't say that that alternating series converges. So overall in number 1, we're diverging. Let's move on to number 2. In number 2, I have -1 to the k times k over 5 to the k. So taking the absolute value of this series, I get the summation of k over 5 to the k. Now, I need to decide whether that absolute value of that series diverges or converges. If it converges, I know I sound like a broken record, but it's great if it converges because that means we converge absolutely. So there's a couple different ways we could decide whether this converges or not. And we could probably either do, looking at this, we have something to the kth power, so I'm going to go ahead and run with the root test. Also try the ratio test because I think you'll get something out for that as well. So I'm going to just run with the root test. So I'll write what test I'm doing right here. Doing the root test, I'm going to take the limit as k goes to infinity of the kth root of the absolute value of my series. But because I already took the absolute value, I'm just going to write k over 5 to the k. Now, whatever we get for this, as long as it doesn't equal 1, then we can conclude whether it converges or diverges. If it's less than 1, if the limit is less than 1, we're converging. If the limit's greater than 1, we're diverging. If it equals 1, we don't know. We're just going to have to try another test. But let's see what we get. So when doing this limit, we'll get the limit as k approaches infinity of, I'll go ahead and distribute this kth root. So I'll get k to the 1 over k for my numerator and 5 in my denominator. I know for a fact that the limit of k to the 1 over k is going to be equal to 1. If you need me to work this out at some other point, leave your question in the comments or feel free to ask a fellow student. Also, check your textbook. I guarantee it's in there. And then we're going to have 1 over 5. Well, the limit is equal to 1/5, which is less than 1. Therefore, I know that this series is going to converge. So because the absolute value of this series converges, this overall series converges absolutely. So we converge absolutely for number 2. And lastly on this worksheet, let's look at number 3. Number 3, throwing some trig at you, but it's really not that scary. Because think about the cosine of something times pi, where that k is just integer values. Well, think about plugging in a k value of 1. That's going to be the cosine of pi, which is -1. And then plugging in 2, cosine of 2 pi is 1. 3, cosine of 3 pi is -1. 4, we're going to get 1, and so on. So you can see that this is just like writing our series as going from -1 to 1, -1 to 1, -1 to 1. It's alternating, right? So k equals 1 to infinity of this cosine of k pi is going to be like -1 to the k. When we plug in 1, we get a -1. When we plug in 2, we get a +1, and so on, all over the square root of k. This is simple enough. Now, let's just take the absolute value of this series now. So the absolute value of cosine of k pi, you can see that the absolute value of that is always going to be 1. So the absolute value of this series, starting at an index of 1, going to infinity, is going to be 1 over the square root of k, which this itself is a p-series. And we know that the p-series has a value of 1/2 because this is k to the 1/2. So since p is equal to 1/2 and that's less than or equal to 1, we know that this absolute value diverges. So because the absolute value diverges, we're going to need to do a little bit more work. But we've eliminated the fact that we're going to converge absolutely. So we're either going to have conditional convergence or we're going to diverge. So let's jump into that AST, the alternating series test. Our a sub k value is 1 over the square root of k, which we can also think of as 1 over k to the 1/2. Now, if you recognize this, we actually did this problem earlier on in our worksheet, but let's quickly go through it now. 1, we're going to show that it's non-increasing. So the derivative of 1 over the square root of k is going to be equal to, bringing that -1/2 down, -1 over 2k to the +3/2. And this is negative, therefore we're non-increasing because that derivative is negative. In part 2, we just got to show that the limit as k approaches infinity of 1 over the square root of k does indeed equal 0, which it does because the square root of k goes towards infinity as k approaches infinity, and that constant of 1 remains the same. So we have 1 over something that's blowing up. That's going to go towards a really, really small number of 0. So by the alternating series test, we actually get that the alternating series itself converges. So if we have that the absolute value of our series diverges and the alternating series converges, in number 3, we are going to have that our overall series converges conditionally. So these were three fairly nice examples, right? In the first one, we got that our alternating series just simply diverged. Then we got that it converged absolutely. And then lastly, in part 3, it converged conditionally. So those are three different cases for converging conditionally, converging absolutely, or just diverging. So hopefully you found this video helpful. Continue tuning in, and I'll be planning some other worksheets and some more example problems. So stay tuned for the next video, and good luck!